So welcome everyone to this event, WIVA P&G Knowledge Exchange on hydrogen trains. My name is Nikolaus Fleischacker from Fenn Systems and the Green Energy Center. I'm the project manager of HyTrain, and today we want to show you a bit an overview of what we did in this HyTrain project and also what's going on in general regarding hydrogen trains in Austria, Europe, but even worldwide. We have the following agenda prepared after some welcoming words from the Climate and Energy Fund, which is funding this WIVA P&G HyTrain project. We will also hear some words from WIVA P&G itself. It's the hydrogen initiative of Austria, a national initiative similar to Hydrogen Europe on a European level, and then also the Green Energy Center will be shortly explained where this event here takes place. After that we come to part 1, where the project members of HyTrain will tell you all about this research and development project, what were the objectives, what was the main research done for, and what are also the results and what can now be used to implement hydrogen trains not only in Austria and Europe but even worldwide. So we give a comprehensive overview of what was done in this hydrogen project. And then after a short break in part 2 you will hear about all the hydrogen trains or the major hydrogen trains developments in Europe, starting with ÖBB showing their results regarding the Alstom Coradia E-Lind, this hydrogen train, which will then be followed by Stadler and their hydrogen train called Flirt H2. A colleague from DLR, which is a bit delayed because he is still in the train traveling to here. So in Germany he had some troubles in Stuttgart. The ICE was broken, so I had to change, but hopefully he will be here in time. At the moment everything looks good. He will show us about a European hydrogen project called FCH2 Rail, where CAF, the Spanish train manufacturer, built a prototype of a hydrogen train. And then also Siemens sent us, we couldn't attend directly, but they sent us some small video where we show also their hydrogen train development, and then the whole session will be concluded by Bosch and their developments regarding internal combustion engines for hydrogen. After each session we will have some short Q&A where you can also pose your questions. So if you have any questions, please, if you're attending online in the live stream on YouTube, please simply use the chat. My colleague next to me will then gather all these questions and we will then answer them in the Q&A sessions after the speeches and presentations. And also, if the chat is not fine for you, you can also send a mail to info@hytrain.at. We will also gather these questions, and of course people attending live can then directly ask their questions. So I don't want to hold you any longer and already give to the next welcome point. So we have Oben Peiker from the Climate and Energy Fund, Manuela Priller from WIVA P&G, and Ernst Fleischacker from Fenn Systems and the Green Energy Center to welcome you to this presentation. And we start with the welcoming words of Oben Peiker, who is leading this energy model regions at the Climate and Energy Fund, funding also our HyTrain project. So, hello Oben.
Hi, good afternoon. Hello, Nikolaus. Thanks for having me. Is it possible to share some slides, or do you want me to just give some welcoming words without the presentation?
You can also share some slides, of course.
Okay, let's try that. I have only 3 very short slides. Let's go quickly through them. Yeah, I think you can see them already. So I think it's good to give some context before we go into the details. So I will quickly start with an overview on what the energy model region is about, where, as Nicolas said, the HyTrain project has been funded. And during the course of the afternoon, we will go into more details, and obviously things will get more and more interesting. I'm really looking forward to the presentation. I haven't heard about the outcome of the HyTrain project in a while, and I'm curious how this will be reflected in the community and what questions will arise. So I'm really looking forward to that. So the energy model region is a part of our funding portfolio. We have started this initiative already in 2017. And since then, we had 3 calls, and the last call was in 2021. So there are new calls. Nevertheless, now is the time when most of the projects that we have funded in the context of the energy model region are producing outcomes, and you will probably see a lot of knowledge exchange in various topics that have been addressed in the energy model region. Quickly, what is the funding program about? It's a very broad funding scheme. It really is about developing and demonstrating model solutions for everything connected to the energy transition, and in parts as well with regard to the mobility transition. And the USP of this program is the combination of research and development and pilot and demonstration. So we wanted to see the development and use of local energy and energy-related transport technology for large-scale field testing. And by that, we as well wanted to strengthen the value chain for Austrian technology providers. And this was, in our point of view, only possible if you are in close link with the end users. So these were the 3 main objectives of the energy model region. Which is it about in a glance. As I said, there have been, or there are currently a lot of projects providing outcomes and results, and there is a lot of discussions are currently going on. Just to give you a few facts on the energy model region, we have funded 3 thematically focused regions. One is on dealing with smart grids, one is dealing with the decarbonization of the industry, and one energy model region is dealing with the topic of hydrogen in a broad sense, meaning transportation, meaning energy system, meaning industry. Manuela will tell you about that in a second. We have provided 120 million euros of funding. And as this is public funding, the private enterprises had to come up with substantially larger parts of investments during the course of the last years. So the total investment volume we expect to see until the end of the last projects will be over 400 million euros until 2028. And overall, the initiative runs for 8 years. And I stopped counting a few months ago, but back then it was already over 300 project partners from industry and science in the 3 energy model regions. I would like to invite you to have a visit of the websites of the 3 energy model regions. I think it's very interesting to see what projects have come out, and WIVA P&G is doing a great job there, showcasing outcomes. And this is a research-focused program, so things can usually develop in different ways, and there are projects where everything goes as expected, and there are other projects where things do not go as expected. Nevertheless, in any case, it's very important to share the knowledge you are retrieving throughout the course of these projects. And I'm very thankful to Nicolas and his team that you are organizing this knowledge sharing today on such an important topic as transportation and trains in particular, and the role of hydrogen therein. So thanks a lot. Thanks for the opportunity to start this whole session, and I'm really looking forward to the other presentations and to the questions that you have. Thanks a lot.
Thank you, Urban. So then we come to Manuela as the next speaker. Manuela, are you already?
Yes,
Okay.
Good afternoon, everyone. I'm Manuela Prila. I'm here today on behalf of Horst Steinmüller, the chairman and of WIVA P&G, and I will tell you something about WIVA P&G and about our green mobility project purposes. So WIVA P&G is an association which was born for the coordination and management of the same named flagship region. We have within WIVA P&G projects over the whole green value chain, and we focuses on green mobility, green industry, and green energy. The projects are from the production of hydrogen over the storage until usage. HyTrain is one of our 15 flagship region projects, which is for sure situated in the field of green mobility, which is one of our 3 fields of innovation. The usage of hydrogen in heavy duty is one white spot, and of course hydrogen is one solution, but not the only solution for defossilization of the economic system. In our point of view, hydrogen should be used there where electrification or the usage of battery electric vehicles, respectively driving units, makes no sense. Very important is always, and that is, I would say, the heart of WIVA P&G. We always look at the whole system. We look at the whole value chain. It's not about one small part. It's looking about the whole energy system. And in this sense, it's not in the focus if the driving unit of a vehicle is using hydrogen. It's always about how you integrate it in the whole system. Sector coupling is very important in this field and should be looked at everywhere. In that sense, I was very quick, but I just heard that I will be here on short notice, and I give back to you, and thank you, Nicolas, sorry.
Thank you, Manuela, for these introductory words regarding WIVA P&G. And that brings us to our welcome to the Green Energy Center Europe, where this event is taking place. And I give over to Ernst Fleischhacker, the founder of the Green Energy Center Europe and also the CEO of Fen Systems and core lead of the WIVA P&G HyTrain project. Thank you. Please.
Yeah. Thank you to Nicolas. Thank you for coming. You're welcome here at the Green Energy This WIVA P&G HyTrain project was developed within this frame, Zillertalbahn 2020 plus energy autonomous with hydrogen.
Becoming autonomous in matters of energy is on its way. Politics and economics are working step by step to achieve this goal. The Green Energy Centre Europe, located in Innsbruck, is a strategic partner and catalyst when it comes to using green hydrogen as a bridge for the energy turnaround. The supervisory board of the Zillertaler Verkehrsbetriebe AG decided to shift to a narrow gauge railway, the first one worldwide, which is a courageous step and a lighthouse project, showing the world that this region is not only a global brand concerning hydrogen, but also in terms of ecological energy.
2 years ago I took over responsibility for the Zillertalbahn, and from the beginning there was only one thing on my mind: using electricity instead of diesel. The electrification cannot be implemented by building a conventional power line through the Zillertal region, but by using hydrogen instead, because there are the big power plants in the tributary valleys. Verbund is running big power plants, so it was clear to me to accumulate this sustainable green energy in hydrogen in order to be able to use it again whenever necessary. This has to be the technology we use in the future.
And that's how it is today. Green hydrogen is produced in Mayerhofen in the Zillertal region and provides energy for the refueling of trains. For the Zillertaler Verkehrsbetriebe AG, this means a conservation of 800,000 litres of diesel, as well as a reduction of 2.2 million kilograms of carbon dioxide emission per year. The project should be implemented by 2022, and its aim is a noiseless and emission-free regular service on the 32-kilometre-long railway track between Mayerhofen and Jenbach. With that in mind, one can feel well prepared for the future.
There is a massive increase in ridership, not only in the tourist, but also in the commuter sector. The trains will be well equipped, so that transporting skis or bikes will be no problem at all. But still, the focus is on providing a quick transfer opportunity for commuters from Mayerhofen to Jenbach and further through the Inn Valley.
The hydrogen project Zillertal, which was developed together with experts of the Green Energy Centre Europe, is implemented with a lot of respect and sense of responsibility. It is also the next step for Tyrol, to use its resources optimally and develop new strategies to be able to explore new opportunities.
Hydrogen gives us the opportunity to model our energy supply in a decentralized way and to accumulate energy. Mobility is a perfect example to show how hydrogen can be used in a reasonable way in the future.
At the beginning, the Green Energy Centre Europe used hydrogen cars for the hydrogen highways and for establishing the first green corridors in Central Europe. The perfect example that using hydrogen also works in the industrial sector is the collaboration with Emprise, an enterprise that agreed to cooperate in the context of an EU project. In Wels, Europe's biggest electrolyzer is built to transform green electricity into hydrogen. The whole of Europe is watching the project. Since this plant is built under economic aspects, it can be proved that using hydrogen instead of fossil energy is also a business case for the future. The first Hydrogen Discussion Board 2018 in Innsbruck has shown in an impressive way how much there is a need of this sort of new strategies.
Many conscious citizens are asking themselves how the current situation with fossil fuels will look like and how to use alternative energy instead of diesel. It is very important that many experts on this field are gathering in Innsbruck today and exchanging their experiences with hydrogen and alternative fuels.
In public transport, experiences with hydrogen fuel cell buses have already been made, showing how to adapt the vehicles for the needs of different regions. The experts of the Green Energy Centre Europe need to stay on the ball to develop new strategies and projects for green industries and mobility for the future.
The Green Energy Centre
Europe stands for building bridges into a future of green mobility. With our partners, which are big enterprises, industries and also startups,
Industriepartner, aber auch kleine Startups, mit denen entwickeln
we want to develop and provide new solutions to a world that is dominated by oil, coal and gas, and change it into a green world, powered by sun, wind, and especially here in Tyrol, water.
Tyrol plays an important role in Europe in terms of strategy formation. This was confirmed in an impressive way at the first Hydrogen Discussion Board in Innsbruck.
Ein Meilenstein nicht nur für Tirol, sondern für Österreich und Zentraleuropa.
It was not only a milestone for Tyrol, but also for Austria and the whole of Central Europe. For the first time, experts from all over Europe met and shared their experiences, especially with buses, and engaged themselves in our resource management. These two different approaches, meeting here in Tyrol, symbolize a milestone for Austria and Central Europe.
Ein Meilenstein sein für die ganze Szene in Österreich und Zentraleuropa. Yeah, and as I told you, this was the framework for developing the WIVA P&G project, which was a research competition project, which you heard before from the climate and energy funds. And our task was to put this project into an environment for a green hydrogen economy, a regional green hydrogen economy. And the main topic was the quality assurance and to develop the parameters for the quality assurance and risk management in the implementation of the hydrogen train. So this was also the background for the development of a holistic business case for heavy-duty traffic solutions with green hydrogen. And with this background, we are working here in the Green Energy Center, still ongoing. And with this background, we will also see the discussion today. So I have the opportunity to say and to wish you a nice afternoon and a fruitful discussion about our knowledge exchange about hydrogen trains. Thank you for this.
Thanks a lot. Thanks a lot for all the welcoming words, also to Urban Peiker and Manuela Prila from WIVA. So we heard that the Climate Energy Fund not only funds hydrogen project, this is a much broader idea. It's about the reconstruction of the energy system in all fields actually. And WIVA of course focuses on hydrogen, but this is not we only do hydrogen, but also always questions itself, where does hydrogen make sense? And especially at the Green Energy Center Europe, as you could see, we researched the power on demand and the power to hydrogen process, which have to work together closely. And also in this view, one can see the HyTrain project. So it's always to question, is hydrogen or the electrification with hydrogen a solution that makes sense? And of course also for this train project, this always was a big one. So let's take the opportunity in part one to get now into more detail regarding the WIVA P&G project HyTrain. We have three presenters, starting with Nusha Shagibinia from Fen Systems. Then we continue with Max Weber from HyCentar, which will give us a more detailed overview of a study result, and conclude with Josef Kometer from Prose. Fen Systems is a project lead, as already told, in HyTrain, and the holistic view on the overall reconstruction was here the main focus. So that's why Nusha will also give you an overview of the project objectives and so on. while Max will really focus on some details, and Josef Kometer from Prose, our railroad competence, will give you the outlook. What can we do now with this know-how? So please, Nusha, come forward and give us your presentation. Thank you.
Thank you very much, Nikolaus, for this introduction. So, I work at FEN Systems, representing the Green Energy Center Europe in Innsbruck. You already heard the introduction from its founder, Ernst Fleischhacker. Since 2014, we have been supporting FEN Systems clients regarding the reconstruction of their energy system towards climate neutrality and energy autonomy in 3 fields of strategy, project and product development, quality assurance and monitoring, dissemination and training. In addition, since early 2019, all research activities are bundled in FEN Research, which is an independent, non-profit research organization focusing on inter- and multidisciplinary systems and logistics research. So FEN Research operates 2 research laboratories, eWest and HyWest, focusing on power on demand and power to hydrogen processes and also the interaction between these processes. Now today in my presentation, I will give you an overview regarding the research and development WIVA P&G HyTrain project. First, by introducing the project consortium, project objectives, secondly, by presenting results, and lastly, by giving you an outlook on synergies with projects and programs for the establishment of the green hydrogen economy in Tyrol and in Central Europe in general. So the proposal for this project was submitted in 2018, and after evaluation and acceptance, received funding from the Climate and Energy Fund, and it started its activities in 2020. This is a flagship project regularly evaluated by independent international expert panel. So the total project budget is around 3 million euros and currently is at the latest stages of completion. Regarding the consortium, as mentioned, the consortium lead is FEN Sustain Systems, who as developers of the commercial Zireh Taliban 2020 plus energy autonomous for hydrogen initiated this research and development project to tackle the higher risks regarding the implementation of a hydrogen train. So the project operator with rail operation competence is Zireh Taliban, Prose with train and railroad competence, HyCenta with hydrogen competence, and WIVA P&G as network coordination is representing the corresponding energy model region. As I mentioned, FEN Systems initiated this project to build up know-how for quality assurance and risk minimization for the implementation of a hydrogen train. So the first objective was to establish the state-of-the-art for hydrogen trains, and that by means of train simulation and test bench operations, and also to develop a holistic hydrogen infrastructure concept. The second objective was to determine criteria and parameters for hydrogen trains and corresponding hydrogen infrastructure for the quality assurance and risk minimization process. And that was regarding tendering, contracting, commissioning, acceptance, operation, and warranty. And the last objective of applying all the findings of this research and development project to the implementation project, which is now foreseen in a follow-up project. So now with the objectives classified, the project developed 2 research teams, one focusing on hydrogen train and one focusing on hydrogen infrastructure. For example, for the hydrogen train, one of the main research topics are the lifetime of the train and also the optimization of the energy consumption, since these 2 parameters has important impact on the operational costs. but also degradation of the fuel cell system health monitoring using real-time recognition state, and also improvement of the operation strategy and optimizations for lifetime efficiency and performance. Regarding the hydrogen infrastructure, so the main focus was the interface between the hydrogen train and the hydrogen refueling station. And for that, a refueling protocol was developed in terms of cost efficiency and time of refueling. So now I would like to give you a broader outlook regarding what has been done. So for example, when it comes to degradation and health monitoring, no device other than cell voltage monitoring is available, where each cell is wired, so the measurement is prone to error. And in HyTrain, we came up with the concept to develop a fuel cell system monitor with 2 sensors for simplicity, and also to introduce new methods of signal analysis, and these are, for example, nonlinear response analysis, time series analysis, and utilization of system cause perturbation. The fuel cell system monitoring hardware was developed in collaboration with the Graz University of Technology, focusing on system integration and software development, but also establishing time series analysis, and in addition also considering adaptation of speech recognition algorithms in this application. Now regarding the interface of hydrogen train and hydrogen infrastructure, as I mentioned, a refueling protocol was developed and optimized by considering an optional pre-cooling. So this protocol is now in place, while currently there are no standards for hydrogen trains. And this protocol can be used now further for the industry to support them in this technology. Now I would like to show you in more detail how this protocol was developed. So first of all, I want to mention that for the pressure losses and refueling time, several parameters were specified in the beginning, such as pressure or the temperature. And here you can see in the left that, for example, the positioning of the nozzles in the train was investigated regarding the pressure losses. And regarding the nozzles and receptacles, for example, 2 types of nozzles were studied, one TK25 and one TK16 high flow. And there was a comparison study between these 2 by considering the organizational time limit of the train use case that we have. So here in the graph on the right side, you can see that we have 35 minutes of time limit for refueling and reaching the 100% state of the charge because of the train use case at our disposition. So now if we use a TK25 nozzle, you can see that we can significantly reducing the refueling time. And interestingly, this behavior is similar to the behavior of 2 TK16 high flow nozzles, which additionally compensate also higher differences in pressure. So now this protocol developed and optimized is at our disposition, ready for use in industry, since it's going to reduce also a lot the cost related to the infrastructure. So all in all, everything progressed quite well in the WIVA P&G HyTrain project until now. In addition to the other studies which are still in progress, we saw that the concept for the hydrogen refueling station is developed. The refueling protocols are available for use. Regarding the energy storage and powertrain system, so the basic operation strategy was developed, and currently optimizations regarding lifetime and energy consumption are also in place. Also some words regarding dissemination, communication, and exploitation. Until now we had 15 workshops, more than 30 citations, and the number of visits on the project website is still increasing. And we will be handling the project website also beyond the project completion. So all in all, one can say that everything is in place for this hydrogen technology to be introduced to the hydrogen trains and operators in a knowledge-based and minimized and risked way. So Ernst Fleischhacker already showed you an insight to the bigger picture. What I would like to focus on is the impact of HyTrain on the European projects that we are currently working on within FEN Research in European Consortium. As an example, in the Most Hydrogen project, where we are investigating novel technologies for the hydrogen storage, we are really using the comprehensive data from HyTrain for the detailed data input, which would not have been possible without HyTrain. Also, many developments in HyTrain are now basis for the difficult build-up of the green hydrogen economy at the regional level, which started with the development of the hydrogen highway in 2014 in the frame of the Tyrol 2050 energy autonomous strategy, where rollout of hydrogen cars along the Green Brenner corridor took place. And the concept for that was developed by FEN Systems for Hyundai Austria. So this project led to the next project, hydrogen or green hydrogen for Emprise, Tyrol, and Europe, which initiated in 2016, which is actually now itself an established green hydrogen economy. So this project is now providing green hydrogen, the first green hydrogen now to Austria and to the Central Europe. Now the third project, the Ziller-Taliban 2020 Plus Energy Autonomous with Hydrogen, as many of you may know, the concept now has changed. Now the focus is on power on demand process and electrification, which is still in line with the Tyrolean strategy, but of course now for the implementation of the regional green hydrogen economy, the most important project and even the most cost-efficient project is missing, with consequences which are not yet revealed. But anyway, we simply carry on. The fourth project of the region is the TWAG project, Power to X Kufstein. So this project also faced some delays, and we are hoping that these are now finishing soon, these delays, since this project, as the last project, is actually very important for the redundancy of the existing hydrogen technology and economy in the region. Currently, with our partners, we are focusing on gathering all achievements in buses, trucks, and hydrogen infrastructure in an overarching hydrogen valley project from Trentino in South Tyrol to Bavaria under the working title H2 Brenner Valley. So if you are interested in joining in this next step, feel free to contact us. Thank you for your attention.
Thanks a lot, Niusha, for this really interesting presentation. Well, we all heard now that a lot of groundwork has been covered within this HyTrain project. So it's not just about generals, but it really goes into the bits and pieces, to the fuel cells. They are measured, the stacks, but also the interface between the train and the infrastructure was of big interest, since this is always something no one in the end is then, which is something always a bit in the air, because there's of course the manufacturer of a train who has to guarantee for that one, who has to issue warranties, and who has to also be safe that what is guaranteed also works out. And on the other hand, there is the infrastructure, and in between it has to work, because in the end, if the refueling or things like this don't work properly, or quality is of an issue from the hydrogen, this immediately goes into a big fight, and a lot of know-how has been build up on these issues to really close the gap, especially for operators. And as Nusha said it, we also carry on. There are the next steps, also in a broader sense, really in a European sense, in the hydrogen highway from Trentino to Bavaria. Also there is a European project forming, so please don't hesitate if you want to be part there and also want to support this project development. This brings us to our next speaker from HySenta, Maximilian Weber. He is a young researcher, especially focusing on comparison of drivetrains in the rail sector. This was a study that has been going on for maybe a bit more than a year, comprising quite a lot what we did in this project. So now you heard from Nusha an overview, and now we go into a bit more detail. What did we do with this data? Max, please, stage is yours.
Thank you so much, Nikolaus, for this introduction. Warm welcome to all participants, also from my side. And yeah, my name is Max Weber. I'm research associate within Hydrogen Center Austria in Graz. And before I will talk to you about scientific comparison of drivetrains in the rail sector, I would like to introduce you to the HySenta. It's a non-universitary research organization at Graz University, which employs more than 90 researchers of different academic background. And our hydrogen competence involves all steps along the value chain, from production to distribution and application of green hydrogen. So, as I mentioned, my presentation is about a comparison of different propulsion systems in the railway. This was especially necessary because the former decision on the hydrogen trains faced major headwind again last year. So we carried out a huge comparison of different technologies and compared these. So why we need to decarbonize is all clear to us. So I don't spend much time on that. Even when the rail sector takes only a small percentage of the carbon emissions, only 58% of the European rail network is electrified. And in light of becoming climate neutral by 2050, these emissions need to be cut down to zero. So the challenge, especially for regional railway, is that electrification via catenary lines is cost intensive and resource intensive. So it's not always the case to use. So this is especially for regional railways the case, because always or sometimes the driving frequencies or the passenger volumes aren't right for using a classic electric train. So here we are. We have some other technologies like the battery train or the hydrogen train, which are suitable alternatives in this. But we need a case-by-case decision on which propulsion systems need to be used, because it always depends on the boundary conditions, which is the best or the optimum technology. So our goal was to build a methodological tool chain for scientific, technology neutral and holistic comparison of drivetrains. And the methodology is based on the following. First, we performed a longitudinal dynamic simulation for all the different propulsion systems to calculate the energy demand based on certain vehicle-related parameters and certain track-related parameters. Second, we collected a large amount of profound data from literature, manufacturers, and experts to quantify, for example, resources, costs, emissions, etc., etc. And for the typical operating period of 30 years for trains, we considered the single life cycle phases of both the vehicles and the infrastructure that is needed to supply the trains with the energy required. And the last one is the multiple criteria decision analysis, which is needed to compare these technologies based on the quantifications from step 2 with regard to several aspects. In this case, it was an ecological aspect, an economic aspect, and also technical and operational aspect. So, as we all know, and I said it before, it's dependent on the boundary conditions. So we need further information about, here in this example, the Zillertalbahn. And I summarized all the track and vehicle parameters on this slide we used for our analysis. And of course, we also need some specifications of the different trains we considered. So I will show all the different trains now. And here you can see, for example, we applied efficiency ranges, the simulated vehicle consumptions, and as the assumed fleet size that is required to operate to maintain the specified timetable. So you can see here, for example, for the battery train, we considered a fleet size that has 1 unit more than, for example, the other ones. Because of the timetable. Yeah, and with all these data we just collected, we can have some results, for example, on the CO2 emissions. And as you can see here, we have not only examined the different technologies, but also different energy sources, such as fossil diesel and renewable diesel or e-fuel, electricity from the energy mix and from renewables, and from hydrogen we considered fossil and renewable hydrogen that is produced centralized and is distributed to the application. And on top of that, we also included hydrogen that is produced in a decentralized way via electrolysis. And also there we considered the energy mix or renewables as their energy source. You can see here the results, basic results is the bar, and both ends of the risk curve indicate the upper and the lower limit we just found in literature to describe the technologies. The results include direct as well as indirect emissions from resource use and energy use over the complete lifetime. And what can we observe? So the operation is the main source of emission in case of we use fossil fuels or energy mix. But when we use renewables, the production should not be ignored in terms of the emissions. So as a takeaway, maybe in the medium to long term, only the use of renewables is suitable and sensible for rail operation. A similar illustration is given here with regard to the costs, but I will skip that partly because I will focus on the final comparison. I will show you on the next slide. So we want to analytical evaluate the drivetrains with the multiple criteria analysis. And for this, we just used a priority matrix or matrices to give a weighting of the different aspects we used in our comparison. So for example, for the ecological aspect, we not only focused on the CO2 emissions, but also on the particulate emissions or the area amount. Of course, in case of the economic aspect, it's the operational costs and the capital costs. In terms of the technical aspect, it is, for example, the powertrain mass, the powertrain volume, the constructional effort, the technological maturity, and maybe the durability of all the components. And last but not least, for the operational aspect, we considered, for example, the driving range, the maximum driving range the technology is able to, the recharging and the refueling time that is able, and yeah, by this we got a diagram that is shown here, which shows the four aspects in each corner, and also here in this diagram we focused on the diesel from fossil diesel, the electric and battery train using renewable electricity, and the hydrogen train using renewable hydrogen produced via electrolysis on site. So as you can see here, for example, the hydrogen train has its benefits, especially in the ecological, in the economic situation. Sorry, not the economic, in the operational aspect, but has its disadvantages in the economic aspect, for example. So, and now when we will use a really final comparison, we need to compare the ecological, economic, technical, and operational aspect. So we use another priority matrix to do so, and this is one example of result we can get from this. So you can see here the electric train is the best in this case, followed by the hydrogen train, and followed by the battery electric train. So to conclude my presentation, I'd like to highlight once more that there is no universal optimal solution for every case. But some important general findings from the analysis are future powertrains should be based on electric machines. Classic electric trains are the best option in most cases, but battery or hydrogen electric trains are suitable, especially for regional railway if the boundary conditions are fitting. But the suitability of each technology depends on the respect boundary conditions, which is why the proposed comparison should be always applied for each rail project. So, thank you very much.
Thank you for this more in detail result of the HyTrain project. As you can see, a lot of input parameters were necessary to make such a comparison of different drivetrains. And we now come to our next speaker, Mr. Kometa from Pose, who will now give us an overview of the know-how for the hydrogen trains gathered and how that can be useful for train operators and also OEMs of trains even. Okay. Joseph, please.
Thank you, Nikolaus, for this introduction. Hello from my side, and I want to explain some more details from our view in this project and some generic factors similar to that what Maximilian already explained in another view. Here a one-pager for Pose. Who we are. We are an engineering and consulting company based in Switzerland, our headquarters in Switzerland, and we are located in 9 offices over Europe. We are doing engineering, consulting, and expert knowledge for rail vehicles, for OEMs, as Nikolaus already said, but in the same way also for operators, maintainers, and partly also for authorities. What are we doing? I understand us as an integrator of systems. We are solving interfaces for our customers. And how do we work? The most important point is we are independent. We are committed to our customers and ourselves and to no one else, because the shares of our company are mostly in the hand of our employees. Showing here the service portfolio. It is split it in 6 pillars. We are serving our customers in the field of strategy. We assisting when purchasing new vehicles. We have a strong group in homologation services to assist there. Of course, a large team of engineers doing engineering in rail vehicles, but then also during service for maintenance and for modernization issues. As you know, rail vehicles have a quite long lifetime and need some modernization during the lifetime. What did we do in the HyTrain project? The one thing is our task was introducing rail vehicle know-how and solving the relevant interfaces between the vehicle and the drivetrain, as well as the vehicle control system. Implementation of engineering to adapt the test vehicle for the hydrogen drivetrain, consisting of a tank, fuel cell, converter for traction, and also for auxiliary systems, as well as the adaptation of the vehicle control system for the test driving. It was not planned for any passenger operation, but for the test drives. After the test vehicle could unfortunately no longer be made available after the project schedule was adjusted as of September last year. The focus then was on the project's main areas as investigation and the documentation. And together we worked on a handbook. One of these aspects, I cannot cover all in these 15 minutes, one of these aspects is the use value analysis, as Maximilian Weber explained just before. One such focus was particularly the development of this UVA that takes into account the most diverse influencing factors for a system selecting, and thus provides a valuable tool for the preferred vehicle design, as you just heard before. And the factors to be taken into account are not only technical influencing factors, but also operational requirements, as well as economic and ecologic. Let me show you one slide as it is published by Allianz pro Schiene in October 23, the last time. Here you see one key factor for considering vehicle technology with the background from the infrastructure. And you see, for example, Switzerland has nearly 100% electrification in their railway network of all routes there. In Austria, the rate is 71%, for example. In Germany, 61%. And as we heard already, all over Europe, it's only 57% or 58%, as Max has it. Maybe that's because this figure is from last year. And this is a factor in determining which technology solution for decarbonization is even possible. Let me show you a few facts from the state of the art. It's what are the possible energy storage systems. Either it's synthetic fuel, it's currently quite expensive. Accumulators, the current standard lithium-ion batteries system is used the number of charging cycles there is limited. In order to ensure a long service life, only a reduced part of the nominal capacity can be really be used in operation. But here the research into improvements is ongoing. Supercaps might have 10 to 100 times higher power density and larger number of cycles, but they have a quite low energy density. And finally, the hydrogen is suitable for generating the electricity using fuel cells in the train. It's very sustainable, especially when using green hydrogen, of course. In this current diagram, you can see now the relationship between energy density in kilowatt hour per kilogram versus efficiency in percent for the various forms of storage. The state-of-the-art of rail vehicles is based primarily on the energy supply via overhead line, as you know, as shown in the two slides before. This results in a tank-to-wheel efficiency, which is definitely above 80% for EMUs. Please excuse that some of these slides are labeled in German language. Again, one more, the energy efficiency and the weight. Here you see the energy, how much electrical energy must be generated in order to have 1 kilowatt hour for electrical energy available in the vehicle. In principle, storage in batteries is currently many times more energy efficient than the production of hydrogen, or then once more again difference for synthetic diesel from electricity and reconversion in the vehicle. And then looking on energy efficiency and weight, we see another graphic, which here we compare the weight of the energy sources depending on the energy available in the vehicle. Hydrogen and diesel have an offset due to the units required for energy conversion, fuel cell or internal combustion engine. In addition, parts for the tank and pipes are taken into account. Approximately 5,000 kilowatt hours correspond to the electrical energy that can be generated from a usual tank volume for a two-part DMU, taking efficiency into account. Accordingly, only hydrogen and diesel can currently provide the amount of energy for really long distances without recharging. And one more comparison here for the energy density in this table. Normed to diesel with factor 1, you see the much lower energy density of accumulator of battery solutions, but a factor of about 2.8 for liquid hydrogen. Hearing these several factors, we can have a look on hybridization or combination of the systems. Since all available electrical and chemical storage systems currently have a lower energy density than liquid and gaseous media, application-specific configurations or modular concepts appear to be useful, unless they are purely electric vehicles with a continuous overhead line for energy supply. Hydrogen trains are basically also battery-powered trains, but just with a smaller battery as for battery EMUs directly. In addition to the requirements of regular operation, disruption scenarios or operational diversions result in important requirements for energy reserves in the vehicle. In addition to traction energy, also a considerable amount of energy is required for heating, air conditioning, auxiliary systems, which on slow-moving routes, especially with a high air conditioning requirement, can be nearly on the same level as for the traction energy requirement. A hybrid drive will usually be larger and heavier than a conventional drive system alone. EMUs, which are expanded to include an energy storage device, are particularly suitable as a basis for such further development. Such vehicles are primarily suitable for extending a train route beyond an electrified track. The range can be increased by recharging stations and on track and by electrification in sections. Vehicles with a fuel cell enable, similar as an internal combustion engine with a generator, a long range due to the high power density of the energy sources. These energy sources can be designed and support the electrical and chemical storage media or as a main energy source. The storage media must be dimensioned in such a way that the braking energy generated is completely stored and the energy generated in the vehicle can be temporarily stored as far as possible in order to operate the fuel cell then at the optimal performance point. A modular design of the drive as well as installation space and mass reserves keep a vehicle open for operations to operate also on non-electrified tracks. I hope I was able to give you a little insight into the numerous factors that influence the design of vehicles and the various aspects that need to be taken into account for a targeted design of new vehicles and for individual operating requirements. We at PROSE are happy to support you in choosing the right fleet strategy, the best concept and investment plan for respective applications. Thank you.
Thanks a lot for your insight in this. This brings us now to the next part, or the final part of part one, the Q&A session. So we have now the time to answer your questions. Some questions already came in. I please the speakers and also Ernst Fleischer to come forward and take your place here in front so that we can then give the questions to you. So let's start with some more generic ones. So to also give you who are here today in person the time to formulate what you want to ask. Also, the speakers, maybe you have some questions regarding the technologies and things that were researched. First, I want to start with Ernst Fleischhacker. If a train operator approaches the HyTrain consortium, what is the most important advice you can actually give? You have now experience over several years. A lot of things went wrong. Some things worked out. What would the most important advice be?
Yeah, and nearly the same as we did it in 2016 when the Zillertal Bahn AG came up with the question to develop a new concept. Yeah, we told them, yeah, we will do it, but in a holistic view. And we did it in this holistic view. You have seen this in the video, which is already 5 to 6 years old. And what I would say today, yeah, if you evaluate such a logistic view on the system, you have to stick on it, yeah, and you don't have to leave it, or no part of the whole chain has to leave it, because we have now the situation in the Zillertal that one financer tells to the railway operator he will give no money if he don't choose an accu train. So, yeah, this is the situation. Stadler, we will hear it today, is waiting since 2019 for the call of the operator for this train. Everything is in place. I think we will hear how far they are with everything. And this was the result of a tendering process, of an open tendering process. There were worldwide 2 competitors. Yeah, Stadler was one of these 2 competitors, and delivered the concept, which we know today it fits. Yeah, but so that was the decision in the Zillertal Bahn, and yeah, I would say you have to stick on this holistic view on the business case, which is driven on the public motivation and also on the, let's say, on the commercial motivation. And the business case for a change, a historical change in the technology cannot be a commercial business case, which is driven only by private industry, because you are also a private industry involved in this workshop. It's not possible. you have to evaluate both parts of this business cases, and nobody in this chain has to leave this target. So, and that is my advice, what I will give to another operator which is interested on this, what we did in the last 8 years, let's say, the Zillertal Bahn, and the last 4 years with the WIVA P&G research projects.
Thanks a lot. Brings us to another question. Yusha, you mentioned that the results of this project already have been used over part of other European projects. What data was needed there, or which results actually?
So we are now contributing in a European project called Most Hydrogen, as I showed on my slides. The concept is on metal organic framework materials to store hydrogen, and there is a hydrogen storage system being developed in this project. We call it MOF storage system, and the idea is to investigate the techno-economic assessment of this MOF storage system for application in the heavy-duty railroad application. So first we focus on hydrogen trains. So based on the data that we have on the storage system already defined in the HyTrain project, we could provide some data regarding the design of this storage system. And then we would also focus a step further on hydrogen trucks and hydrogen buses to see if this is possible. So in this project, we are working closely with Italfer, with the Italian railway sector. We are closely collaborating on the data exchange basis, and we are also working on the infrastructure concept with them to compare, let's say, the conventional hydrogen refueling station system infrastructure with a MOF storage system. That's the idea.
Thank you, Nusha. So maybe we come to Josef Kometa. You were actually one of the first also joining this project. The HyTrain has a really long history. We already heard 8 years of project development. A lot has happened. If we would tell everything that was going on over the years, this would take, not just this day, but you already, when the project team formed, you decided to be on board. And what was your personal interest in the project? Why did you also decide to put money on it? Of course, we got some funding, but in the end, it's also a big investment for a company.
As an engineering company, Prose is doing developments. And we are always interested in new developments, in new technologies. This was the main factor why we wanted to be involved there and be part of this project. At the very beginning of this project, or before start of the project, it was already a quite new technology. Hydrogen drivetrains had been quite new in the rail vehicle area, and something has to be developed. But in the meantime, the development went on quite fast. And now there are a few OEMs offering hydrogen-powered trains. We will hear later on a few things about. And so I think it's very important for new developments, be nearly in the front of new developments always, to be part of it and to bring in all the experience we and our team has in this field.
Thanks a lot. Max, currently also some research is being finalized and concluded. What is it actually? What's going on at HyCenter?
Well, in regard to hydrogen trains, for example, it's a bit complicated. So for sure, as I mentioned before, it's dependent on the boundary conditions. But we are not limited on trains within the hydrogen center. So we do a lot of research with regard to electrolysis, to infrastructure, so the distribution, for example, of hydrogen, and of course the application in different of vehicles, like mining vehicles, for example, trucks. So there's a lot of work we can do.
Thanks a lot. There has also been a specific question to your presentation, which says, hello, is there already a BEMU, so a battery electric multiple unit with 1000 kilowatt hours of battery pack on the market, or is it only a hypothetical case for calculations?
It's only a theoretical application we just used for our comparison. So as far as I know, there is no electric train, battery electric train with that battery capacity on the market, especially for narrow gauge systems or railway. There is no battery electric train available on the market.
That's always a not so dangerous to say something, since we have Stadler here who are specialized on tailor-made. So I guess if we would tell them we need one, it may be even available, but maybe we can conclude on that later. Josef, comment regarding battery sizes. Do you have what's the current stage with the big manufacturers? Do you already have a feeling for that? Or ranges, if we say ranges?
I think, as you said already before, it depends on several factors. There is a possibility for large battery packs, of course. Then it's the question: is it necessary for the use case running there? I'm sure maybe Stadler can answer this. They are able to deliver nearly each solution what's required. But does it make sense? Does it make sense for a short distance to have enormous large battery pack, which has to be accelerated and decelerated on each stop? So it has to be found really for each application a best solution with size of batteries on the one hand, and the other infrastructure on the other hand.
Thanks again.
May I follow up the question?
Yeah, please, that would be great.
Thank you, Mr. Weber, for a really great presentation. I really enjoyed that. And it was also on the 1 megawatt hour battery storage. Did you estimate the actual weight of the vehicle? And that was suitable for the axle loads on?
Partly. So we have considered a 4-part train with I think it was in 2 parts. We put the batteries in, so it more or less is suitable to put it in when we are limited to about 20 tons per X. Yeah. So when I remember it correctly, it was up to 30 tons.
Excellent.
No, the batteries. Okay. For LTO technology.
Okay, I think that qualifies in the end for has to be clarified with the OEM, with the manufacturer of a train, if it's feasible. Because what I learned in this project is that especially this narrow gauge, it's extremely complex and it makes a lot of problems, and you need some partner that really knows what he's doing. Actually, that was also a big thing already when making this first tender. We also had some other, or for this commercial project, there was not only Stadler giving in a bidding, but also others. But it was clear that Stadler is the only one who will be capable to do it. So for this narrow gauge, what I learned, this is really a big issue because there are a lot of details where not a lot of manufacturers have know-how how to do that. So in the end, I would say our study is more on a general view. As already said, if the 1000 kilowatt battery would be available. Okay, is it generally feasible? But if one goes into details, maybe it looks differently. I want to come also to another question, because it was stressed now quite often that this Zillertalbahn and even was a business case. In which way was it a business case, and how can that be understood? Was it the cheapest option, or want to pose this question to Ernst Fleischacker?
Okay, a business case in a holistic view cannot be, let's say, a purchase comparison only of purchase. Only use purchase parameters. Yeah, a business case must be driven also with public parameters, and so this business case, a holistic business case, contains, let's say, an economic point of view and also a public point of view, and these both cases together give a business case for a hydrogen train, or let's say for a new concept for such a narrow gauge railway. Yeah, because what I learned now here, this electrical concept has to be developed from new, and you have seen in our video that was a concept for Zillertalbahn 2020 plus energy autonomous. Yeah, autonomous means autonomous for this company with hydrogen. And now we have an electric or battery solution, or the operator has to have, let's say this. And what does it mean? Yeah, he has to get his power from the international power plug, let's say. That means power on demand pure, and that's not autonomous. That's extremely dependent. Yeah. And what we developed there was an independent system, which where they have their own hydrogen, own green hydrogen, and with the backup of the green hydrogen economy in Central Europe. So this is different. And if you look at the time frame, we could have our train every day, I can say. Since 2022, we are operating with a electrolyzer. We're producing here in Tyrol green hydrogen. We have a complete hydrogen logistic. You can put your train tomorrow on the Zillertal railway and change the diesel train sets. And with the new concept, yeah, don't know how long they have to wait when it is developed. So there I'm surprised now about your statement, Mr. Weber, and yours. Let's say I'm negatively now. In the emotional point of view, after 8 years the project development, and after this whole thing what we made with the research project. Yeah, so I will stop now, because it's not on me to criticize the decision of one of the financial givers, but yeah, I will do the best to support this. But this project is now a decarbonization project and not an energy autonomous project, in the sense of Tyrol 2050 to be energy autonomous to the year 2050. That I have to state after this round here now officially.
Thank you for this. I guess we cannot go into much more detail regarding the commercial project, which is quite complex in itself, and which had some dynamics. I think Nusha Shakibinia, she summarized quite well when she said, okay, it's now not there, and this will have some consequences that are unforeseen, what this means, but of course the future will show. One question to when you asked came in regarding when hydrogen trains, the efficiency is so low, and they need much more energy. How could that ever be a business case? Maybe that's a question I will answer myself, because that's something I spent quite a lot of time. And in our, or especially in the beginning of HyTrain, we researched that quite a lot. Where does the resource come from, and what are the energy prices? And there, of course, one must state there is the price for energy, and there is also the price for grid fees. And especially when one uses hydrogen, we develop different business case scenarios. It is feasible to integrate hydrogen production into a power plant. So you have something like a direct line and you don't pay any grid fees. And this was really interesting, that when we started, we saw that, of course, we need more electricity, so the price of energy is higher, but we save grid fees, and the saving of grid fees compensates the loss of energy, or the more use of energy. So from the capital, or from the operational costs of energy, there was no big difference between the use of energy from the grid or the use of energy for the production of hydrogen. That was quite an interesting case for myself back then. Of course, now in the meanwhile, this changed a lot because of the energy prices that developed as they developed. But which maybe brings me to one last question regarding the development of power prices or electricity prices in general. Is there anything one can say that helps us for future estimations? I think this is something I can also ask to Ernst. Yes.
Yeah. Okay. It's easy. If you are on the plugin of the international electricity market, you can read it in the last few years. There was Corona. What was with the electricity price? It was cheap than it was never before, because the demand on electricity and on energy in general and electricity went back. So 1 year later, Ukraine crisis came up, energy crisis came up, the electricity price was high as it had never been before. So I guess the decision for the Zillertalbahn was made on these prices, yeah? Because these prices say that the price for energy for producing hydrogen is also high, yeah? But now, 1 year later or 2 years later, the price for electricity is cheap again. So we produce hydrogen, green hydrogen, in the Enterprise facility with, let's say, extremely cheap power. With an extremely cheap power price. That's the situation now. So, and if you make decision, a long-term decision, as the decision which was made here for the Zillertalbahn, yeah, you have to take in account. You cannot make a moment analysis. Yeah, you have to make, let's say, a benefit analysis, how Mr. Weber has shown it. But it's also not, as you heard from him, a holistic view on the whole system. So it's only a benefit analysis with some boundaries. Yeah, as he mentioned. So I wrote it down when he presented this. So, and long-term decisions had to be made, and I repeat myself, with a strategic partnership which has a target, a clear target, and which have to stick long-term on this strategic target, and no part of the chain has to leave this process. Yeah? Otherwise, you will start from new, as we learned today, to have to do it in a Zillertalbahn train. So I heard the train will be opened in 2030 and not 2020, so that means 10 years, 900,000 liter diesels and let's say 2 million CO2. And what this means for the calculation and the business case, don't know. Who has calculated this? Don't know. So, is this enough?
I think that's good enough. Do we have some more questions from the audience here or the other speakers? Okay, then I suggest to have a short break until 1500, and we will then meet again here and start with session 2 and all the speakers. So we have 4 presentations there. Then in part 2, covering the whole value chain regarding trains. I think this will be quite interesting because then it's not about research but really about products, tests, and what has been really done and what's on the rails in Europe and going on worldwide. Thank you, see you soon. Welcome back everyone to part 2, hydrogen trains in Austria, Europe and worldwide. We have 4 presentations pending. From ÖBB, Lars Behrendt, Stefan Bernsdorf from Stadler, Holger Titus from DLR and Roland Fortenbach from Bosch. We will hear all about the 4 main hydrogen train developments in Austria, starting with Lars Behrendt from ÖBB, giving us an insight of the Coradia E-Lind that was in test services on the ÖBB tracks. Thanks a lot, Mr. Lars Behrendt, for your presentation.
Hello, my name is Lars Behrendt, and today I will talk about our experience with hydrogen operation and battery operation at ÖBB Personenverkehr AG. My agenda today is a short introduction about the department fleet management, a short capture of the ÖBB climate strategy and some data facts. Our focus at ÖBB Personenverkehr and a short overview about our decarbonization projects, Project CityJet Echo and Project Island Operation. Some conclusion, advantage, disadvantage, and the forecast. We are in the fleet management department at ÖBB Personenverkehrs AG, and who we are the vehicle holder and have the responsibility for the fleet management. We have the responsibility for the coordination of the maintenance. We set up the fleet strategy ongoing, and we have also the responsibility for the rolling stock tenders and the rolling stock project, and as well we introduced new fleet innovations in ÖBB passenger service. Some data facts about the ÖBB. The ÖBB is the largest climate protection company in Austria. We have the goal in the mobility sector carbon neutral by 2030 and about 80 million fleet kilometers each year we have in passenger service, and approximately 25% of that we have a diesel traction in the commuter rail. And one solution to reduce the diesel traction is to use alternative traction on regional railways. If you talk about alternative traction, we have to talk about the solution. We have at first the battery trains, we have hydrogen trains, and we have the electrification. For us as ÖBB Personenverkehr, we have to focus on the first and the second solution because electrification is a topic of an infrastructure manager. We was considering both solutions. Battery trains we was operating a whole year, 2019 and 2020. And we was operate on the most diesel tracks in Austria. The second solution was the hydrogen train, the island, in the year 2020, a couple of months. That was our focus at ÖBB Personenverkehr. We was evaluate the most diesel tracks in Austria, and one specific case in Austria is that the most lines starting from the main line. That means I have still every starting point I have an electrification line on my diesel operation. A short overview about the ÖBB CityJet diesel mainline project. This was a cooperation with the manufacturer Siemens Mobility, and it was a standard CityJet ÖBB electronic unit, and the Siemens was adding some battery packs on the roof and a chiller, because the middle car of this coach was very at the roof was very empty, and so it was available to add some additional battery power packs. Our second project was the operating service of the island from the customer Alstom in 2020 for a couple of months, and we was operating in the rail hub Wiener Neustadt. Why Wiener Neustadt? Because Wiener Neustadt 5 or 6 lines of diesel traction going out from Wiener Neustadt, so it's very designated for evaluate the hydrogen trains. And some facts about the hydrogen train. We was operating in the test case about 15,000 kilometers in 84 days, and approximately 3,000 kilo hydrogen we was using. Let's talk about of the hydrogen fueling station. The hydrogen fueling station was a setup of a container and a truck, and it was a mobile station with liquid called hydrogen, and the storage at the vehicle was about 350 bar pressure. If you talk about the chain, efficiency chain of hydrogen, we have to say we have 75 loss energy from the generation until the wheel, because we have about 35 loss energy in the generation of hydrogen, and we have about 40% loss energy in the rolling stock in the traction. And that is one fact. The second aspect we have to consider is the carbon footprint of the electricity mix. For example, in Austria, we have a lower carbon footprint in comparison to Germany, because in Austria we have a lot of water plants energy generation. And also we have to compare the total cost of energy, and there we know that the hydrogen train is the most expensive in the total cost, and if you say our diesel traction is by 100%, and ATV is as well expensive, because if you consider the electrification of the lines, you have highly cost. I think approx 1 million each kilometer cost of electrification of a line should be calculated. If you compare each technology, all three technology, we can say electrification is low cost in operation. You have low energy and low maintenance, but you have a high investment for the electrification if it's not electrified. Additionally, you have the maintenance cost for the contact lines. Battery train, you have no contact line maintenance. You are energy efficient. All three are energy efficient. Battery and electrification. But you have a limited range. But you can solve the problem with a limited range with partial electrifications, maybe in station or some kilometer of the line for recharging. The main challenge is to develop charging infrastructure, especially in small villages, because they have not the infrastructure to supply a lot of energy. And also for us as operator is the challenge the charging times in the operation plan, because each change of a operation you have standing time for recharging. Hydrogen trains. One advantage is the range of the vehicle, because you have approximately more range than a battery train. But as well, you have a high operation cost. As ÖBB Personenverkehr, we can say, we have an ongoing update of our fleet strategy. In 28, we consider with 16 battery trains in operation, delivered by manufacturer Stadler, and we are still evaluation of solution for existing diesel rolling stock, and in the year 24, today, we are testing HVO fuel because we need as well a solution for our existing rolling stock fleets. If not any questions, then thank you very much for today and for listening to me.
Thanks a lot for this insight on ÖBB operations, also including hydrogen. If there are any questions, of course, we will also try to answer them in the Q&A session later. And that brings us to Stefan Bernstorff from Stadler Rail, so a real OEM, train manufacturer, who will tell us about the Flirt H2, which is already in live operation. Thanks a lot for coming here and giving us an insight.
Thank you very much, and thank you very much for the opportunity to talk a little bit about this quite interesting and challenging project we started in 2019. Maybe for setting as well, I will explicitly talk about the Flirt H2. It is the first hydrogen vehicle we've built. It is actually not in commercial operation yet. It's planned to go into operation this year. I will not talk about other ideas, projects, and what else is happening with Stadler. If you have questions, if I can, I'll answer them later. But this will be solely on the Flirt H2. Besides the color, there's a couple of interesting parts around the vehicle, and this was after less than 3 years from signature with a client to deliver a hydrogen Flirt to them. So a pretty fast-track project we did there as well. But I will first talk a little bit about what was the framework, the setting under that we developed this project and brought it to life. Then more explicitly some of the key requirements that were given us. And then the solution, I'll talk a little bit about the propulsion concept that we decided upon, and then about a couple of systems that are in the vehicle. Setting. The client is in the greater Los Angeles area. This is a not untypical picture of Los Angeles. The air quality is horrible. It's really bad. They are quite unfortunate with a big mountain range, a bit inland, and the predominant westerlies, they really push the bad air in, it stays there, and it's very, very hot. Also, part of the setting is in California, they were always on the forefront of the strictest environmental protection laws. Car manufacturers know that. but it also goes to train manufacturers, industry, and so on. So California is quite special in that. And they also have public funding available to mitigate the not so good air and water, and they've got a couple of other challenges as well, but also air quality. For the setting, this is the LA area, and San Bernardino is about 100 kilometers from LAX airport. It's a bit inland, just at the foot of the mountain range. And this is where the bad air really gets stuck. And because it's inland, it's even hotter. So the specified ambient temperature we had to design to was 49 degrees Celsius, and they do get that. So that is pretty challenging for designing a train, because auxiliary consumption does scale with ambient temperature, especially for air conditioning, especially in America, because they like it nice and cold in the trains. Here you can see, I have to click here. This area is specifically what the client wants the vehicle to operate on. It is actually a new rail service they opened or reopened. There was a rail alignment in the past. They reopened it in 2022. They got 3 diesel multiple units from us. So they are very new. It's a fairly short track. It's 14.5 kilometers. It's 5 stations. It's quite urban, so it's a lot of road crossings, 26 crossings. You can't go very fast. Maximum speed there is 50 miles an hour. And each vehicle at peak days is supposed to do 16 round trips. That translates to 460 kilometers for each vehicle on a day. And also for the setting, the San Bernardino County Transport Authority, SBCTA, they started a study with Michigan State University and a couple of other institutes, quite an extensive study trying to evaluate, very similar to what you're doing as well, what are the different traction systems and what is the best solution for the overall system for their specific application. And they concluded by a very close margin that a hydrogen fuel cell battery hybrid train is the best solution for what they want to do. In 2019, the state of California granted $30 million to SBCTA. And that was allocated for development of the project and getting a vehicle and the associated infrastructure. One very clear condition was the vehicle has to have 0 emission of harmful substances. So that excludes hydrogen combustion engines because they still have harmful substances. They've got small amounts of NOx coming out because you use ambient air in the combustion cycle. It also would exclude HVOs or any other combustion internal engines. So it was down to various combinations of battery, overhead power, and hydrogen fuel cells. Based on that, the client, they put together a very competent team. Different consulting companies that were actually forming part of their technical team. Very professional, and we've been working very closely together. And they started with putting the requirements for the purchase together. This is just a couple of highlights. Altogether, it is over 2,000 individual technical specifications we have to fulfill and prove that we have fulfilled them. But on a high level, the vehicle we are delivering to them has to be identical to the diesel units they just got, except for the diesel stuff. Take the diesel out and put hydrogen in. But everything else, wherever technically possible, keep it the same. Which translates to more than 80% of the individual articles we integrate into a train. Seats, windows, air conditioning unit, the driver's cab, except for a couple of small details. The exterior, the car bodies, the bogies, all is identical. Another requirement was the train has to be able to run the entire day under the worst possible conditions without refueling during the day. So only once refueling in 24 hours at night, because during the day they want to have a very regular shuttle service. That was one of the bigger challenges, because it then drove our sizing of how much hydrogen do we have to have as inventory on the board, on the train. Another requirement was a maximum of 30 minutes of refueling has to be possible, and the target was 15 minutes of refueling for however much we take. They didn't specify the kilograms of hydrogen we have to take, but however much we take, 30 minutes maximum. I did mention the very high ambient temperatures, and also the vehicle has to be suitable to also drive down from San Bernardino to LA Union Station, the old central station in Los Angeles. That is about 100 kilometers, a little bit more, and it's got quite an elevation change as well. That was what we were given, and we then, pretty much in line with what the client had in their heads, decided, okay, the center part of the multiple unit, where we normally have our diesel generator sets, this is what we will mainly touch upon. We did a unusually long concept phase. Normally we get a contract and then we execute as fast as possible. In this case, we took much longer time to really evaluate what is the best concept for that vehicle and what other requirements do we have internally. Because the Flirt is a pretty well-selling product we have. It's a family of single-story commuter trains. I think we have 2,500 and something sold already, all over the world, except for China. And the drive systems, they differ as well. So it's a bit like a Lego building block. You can have a 2-car consist, up to a 12-car is the longest we've done. You can have overhead power, diesel, you can have hybrid, overhead and diesel for range extender, you can have batteries, and now you can have a hydrogen fuel cell system in there as well. What we also decided is we want to have it scalable. So for the different clients' needs, we want to have more power available or less, and we want to have more inventory of hydrogen or less. So we really wanted to follow the philosophy of we have a modular building block for different clients, for different projects, and that took a little while, and I think it was really well invested time we did there. To conclude the overall requirements, this is really just copy-paste from the diesel vehicle. You can see roughly the seating arrangement, the number of seats. That was actually required for us to deliver. What it translated to after the concept phase was in the center part, which we call the power pack, we will have all the hydrogen containing systems. So the hydrogen storage, the hydrogen fuel cells. Hydrogen is not distributed over the different cars, it's only in that one vehicle part, in the middle part. On the roof of the end coaches, we have the traction batteries. That was quite elegant because we had enough space on the roofs available of the diesel units to add batteries sufficient for that hybrid vehicle. And the red marked areas, that is pretty much unchanged from the diesel unit. As I think all of our vehicles, they are actually electrically driven. They all have electric drive motors in the bogies, in the yellow marked ones. They have a motor per axle. the traction converters, wherever the original energy is coming from, brings it down to the bogies. Another way to highlight what we're doing as an architectural layout, we have the hydrogen storage system in a pressure range between 20 and 350 nominal working pressure. We can't go lower than 20 because of the type of tanks we're using, otherwise they get damaged if we drop the pressure too low. We then have a pressure reduction unit to go down to the working pressure of the fuel cells. That goes then to the DC-DC converters, to the central Zwischenkreis at 750 volt, and that goes to the traction converters. And on the other side, we've got the traction batteries, also hooked up to the traction converters, and that then goes to the traction motors. The power and tractive effort and maximum speed again is similar to the diesel multiple units because we have to run the same schedule as well. On the fuel cells, we have 100 kilowatt units, several of them in the vehicle. And I'm sure most of you know that in pretty much in detail, comparing a little bit how a diesel motor behaves in terms of efficiency over its working curve as opposed to the fuel cells we're having here. And that's the two cases, beginning of life when they're brand new out of the factory, and then end of life, wherever that's defined. It's a gradual slide. They degrade over time, as we heard before today. But they behave quite differently. You want to run the fuel cells at quite a low power because it is quite efficient. And that again drives how many units do we want to have in the vehicle versus what is the investment and what is the operational cost. If we run them very hard, we replace them quite often. They are not particularly cheap. The prices are coming down, but still it's an investment. And there was an interesting exercise during the concept phase as well, finding the right balance there in terms of what power do we install in terms of fuel cells. On the storage, that was very interesting for us as well because we had nothing to do at all before with high pressure gases or hydrogen. So for us as a vehicle manufacturer, that was complete new, which for all the engineers was fantastic because they love new. And we were really on the very steep end of the learning curve there. Decided quite early on type 4 tanks, which is non-metallic tanks. They have a HDPE liner and carbon structure on the outside. If you ever have a chance to visit a manufacturer of those type of tanks, please do. It is meditative watching them being wound on the liner. It's fantastic. It's a high art as well. They are 2 meters tall, pretty tall. They weigh about 100 kilos each. And we've got a number of them in the vehicle. And again, it's scalable. To put more in, the center power pack can be made longer or shorter. And we can put more inventory into the vehicle. Refueling, again, complete new area for us. Fueling with pressurized gases, didn't know anything about that. And with our partner, with our supplier, we did quite a bit of modeling as input then for the operator and owner because he's responsible for the fueling station. So we are really focused on the vehicle. But of course, there's an interface to the refueling. We can't do it in complete isolation. Since the fueling station wasn't defined at the beginning of the project, we were trying to give the best possible input into designing and specifying the fuel station system later on, especially in those high temperature areas. And the requested quite fast refueling times, 50 minutes is very fast. We had to look at how much pre-cooling do you need in the fuel station, and that drives again power consumption and cost investment. So 30 minutes for 20 degrees plus minus ambient temperature. We did see that won't be a problem for our vehicle without pre-cooling. So there you can install a not overly complex fueling station. And 30 minutes at night when you don't have operation, that's fine. If it's hotter still at night, and that does happen, you might have to refuel a bit lower. The reason is the tanks, especially the HDPE liner, they do get damaged if they reach a temperature above 80 or 85 degrees. So you really need to limit the temperature, otherwise you have to take all the tanks out and put new ones in. And that's very easy with our system, of course. It's very maintenance friendly, but it's very expensive. It's a lot of tanks, and you really want to avoid that. We also looked at the 15-minute refueling at the worst possible midday, 49 degrees Celsius temperature case. That is possible, but you have to have massive pre-cooling units. The temperature is way in the negative degree C. I don't know by heart what it was, but it was quite cold, but the flow rate going through is quite big, so the cooling units are substantial. We started off after the vehicle was built and showcased at the InnoTrans railway fair in Berlin in 22. We started testing in Switzerland. We found one of the very few tracks that is not electrified and not operated on a regular basis. And we did test runs on that for half a year, a bit more, to really validate the concept we developed on paper and then put together in hardware. But we had no experience at all how the vehicle would work, how it would behave. With a hybrid mode, you have quite a lot of degrees of freedom. We had to be sure that it isn't going completely sideways. So we did some test runs with hydrogen in Switzerland, and there's no infrastructure for that, especially for railway. So we looked around what options do we have to actually fuel the vehicle, and decided upon the probably simplest solution we could find, which is a trailer. You can see here on the top left with lots of bottles inside. They contain about 1,000 kilograms, a ton of hydrogen, pressurized at 300 bar, so less than our working pressure. And the refueling we did with a fairly simple valve station just by overflowing. The trailer had several cascades of bottles, so they weren't all manifolded together, so we could drain the first cascade and then top up with the next one, and did that several rounds. Took very long, had to be very patient, which was actually good for our testing setting, because the most we do in the early phases of testing is on the software side anyway. So the engineers are sitting inside the vehicle and analyzing all the data we gathered from the last run, and then if you have 2 hours, and we had more than 2 hours sometimes of refueling, there's plenty to do. For operational purposes, that would be completely unsuitable. But for testing, especially in this low mileage kind of testing we started off with, that was quite suitable. On the top right, you see the fueling nozzle, again, quite new for us. We saw it earlier, one of the standard nozzles, very expensive, by the way, and they don't last forever. They're quite fragile. And you have to ground the vehicle. You don't have a grounding via overhead wire or anything. And you really want to avoid any ignition sources, especially with that much hydrogen in the vicinity. And then you connect it, it's fairly easy. Open the valve and let it overflow and wait. There was a brief overview of what we've done with that vehicle. In the meantime, we did actually test one of the scenarios as well. How far do we get with one tank filling? And we tested the best possible case. So not a lot of people in the vehicle, nice low temperatures, but not too cold. And we did that in Colorado on the test ring in Pueblo, and drove for 46 hours in a row, the 2,800 kilometers, and still drove back to the fuel station. So we didn't need a tow. We just did complete laps and then decided, okay, that's it now. It's been on 0% gauge now for a while. Let's go back. But that's kind of a validation of how far can you get in a best possible setting. And it was reasonable. I think the average speed was around 60. So it wasn't like creeping at 20 kilometers an hour either, which would be quite meaningless. We did that mainly to gather more data on performance of the vehicle. We did the same then for a typical run with accelerations and stops and respective speeds to validate our simulation models that we did in the beginning. And it was pretty spot on. A little bit disappointed still. The modeling guys, they said 2,800 kilometers. We did 2,803, so they have to tune the model a bit better, but it was close. Well, that was all for now from the Flirt H2. As I said, it will go into operation this year. And that'll be very, very helpful for us as well to learn together with the operator how best to set up the vehicle, the different modes of freedom we have between battery and hydrogen, and what to potentially improve for future projects as well. Thank you very much.
Thanks a lot for your presentation. That was really impressive how serious you take this task and also how much testing is needed to get something like this operational. That was really interesting for me also to see all that and get quite a even detailed, I think even the most detailed view at this train that is available now, because I also saw some of presentations of your colleagues. Thanks a lot. I guess there will be also some questions regarding this train. Looking forward to it. So we come to our next presentation, development and demonstration of a bi-mode fuel cell train in the EU project FCH to Rail from Holger Ditus. I give you the microphone. And fun fact, already discussed in the beginning, it was also considered to participate the same call with our train. But really impressive what you already did. So please, stage is yours.
Thank you for the introduction and for the opportunity to talk here about this European project. Maybe let's check here. Okay, so I'm going to talk about the development and demonstration of a bi-mode fuel cell train, which is a difference to the Stadler train that we have seen just before. How comes that DLR is talking about this? We are German Aerospace Center. Of course, we are talking about aeronautics and space, but we are also doing energy and transport as one of our, or as two additional research fields. And as a whole, in DLR, we do a lot of hydrogen research already. So we used it as propulsion fuel for rockets, but we are talking about generation of hydrogen, like shown this morning already, I think, or in the beginning, about storing hydrogen, about using hydrogen in the end in the mobility sector, and this is where I am working on. I come from the Institute of Vehicle Concepts, one of 30 institutes, and this is one of the pure transport sector institutes, so we are working on starting from bicycles to trains, everything that has wheels is on us, and one of the topics is especially alternative drives in all these technologies or in all these vehicles. Coming back to the topic of railways, why do we talk about hydrogen in railways? So in Germany we have at the moment like 2,900 diesel multiple units that are there, so the CO2 of these ones, the CO2 emissions is quite high, and this is the point where electrification is often not the most economic thing, so we need to think about different solutions. Another topic is shunting locomotives, so 2,800 locomotives in Germany. Average age is 42 years, so you can imagine it's not the newest diesel engines that are used there and maybe not the cleanest ones. So it's not as visible as, of course, passenger transport, but anyway, we need to do something. And we had the chance to send a proposal for a European call, which was coming out from the Fuel Cell and Hydrogen Joint Undertaking, which is now Clean Hydrogen Partnership. And it started in 2020 to prepare the call, and the project we won in the end started in 1st January 2021 for 4 years. And we are a consortium of 8 companies and partners. We have Toyota as a fuel cell manufacturer in the consortium. We have CAF as the train manufacturer, who is one of the biggest partners. We can be glad that we have Renfe as an operator who provided a train that we can use as a demonstrator. We have the 2 infrastructure managers from Portugal and Spain here, so this helps us of course, for all the authorization topics and driving on the public network. We have the National Hydrogen Center and DLR as research organizations, and Stemman, part of the WAPTEC company, which is on the one hand working on pantograph topics, and on the other hand, Favile is working on climate topics. Because we have some of the objectives also think about finding additional solutions to use waste heat in fuel cell drives, and also to use other hydrogen-driven HVAC components in the train. The most important objectives in the project are to develop, build, test and homologate a multi-purpose fuel cell hybrid power pack, and to demonstrate it in a bi-mode CVR multiple unit. So on the left-hand side, this is kind of such a power pack, how it could look like. And on the right-hand side is the train that we defined in the beginning where we want to integrate it. I just jump over that one. We started to evaluate all the requirements for different countries, in that case for Spain, Portugal, Germany and Slovakia. So we analyzed the diesel lines that are currently used and the typical services there, and then we choose the most important services which are either going in special slopes, very high altitudes, or high speeds or high ranges that are needed. And from these analysis of boundary condition and requirements, we derived the requirements for this fuel cell hybrid power pack. DLR was engaged here in doing all the service profile according to EN 5591. And we also started in the beginning with thinking about the H2 refueling. So there are different options on the train. We could go for 350 bars, 700 bars, or liquid hydrogen. Here in that case, we decided to go for 350 bars, but it's also a question of how to supply hydrogen to the train and what is needed as a hydrogen refueling station. And as you said before, in Switzerland, there is no adequate infrastructure for hydrogen refueling. We had more or less the same problem in Spain, and it's not easy to rent something, so it wasn't the goal of the project to develop a refueling station, but we had to in the end, because there was nothing available that we could use. Okay, the fuel cell power pack itself, the idea is to have it scalable and modular so that we can use it not only in this specific demonstrator train, but also in locomotives, in shunting locomotives, and as a refurbishment product for other trains that, well, come to the end of life or have already electric drive by diesel and shall be reconverted. The components come, as I said, from Toyota, the fuel cells. The energy storage system comes from CAF. The DC-DC converters also from CAF. The energy management system, which combines the driver assistance system with the controls of the hybrid system, is also made by CAF, and the cooling systems and the storages for hydrogen are third-party products. As you mentioned shortly, the energy management in such a hybrid thing is quite a complex topic. So this is taken from the EN50, from an EN norm. On the right-hand side, you have all the consumers. So tractive effort, clearly traction equipment is consuming a lot of power. But also the auxiliaries and the HVACs are consuming power. You can get some of the energy back during braking. So if you have a pure battery train, it would be a configuration like this one, where the battery is doing everything. In case of a fuel cell hybrid, you have in addition the fuel cells that can do something, and now you need to choose who is doing what at which time during the operation. But not only during the operation, also when you build the system, when you design the system, you have to think about which amount of power is coming from the batteries and which is the amount of power that comes from the fuel cells in the end. In our case, we would also have, as we are a bi-mode train, we also have the catenary and a pantograph there. So it's not our intention to use all three of them at the same time, but the batteries are charged during operation under catenary, and we can drive and use the overhead line with that kind of train whenever it is available. The challenges are, as I said, the design and dimensioning of fuel cells and batteries on the one hand, and on the other hand, how to work with them if they are built in the train, how to operate them properly to reduce the energy consumption. From DLR side, we developed two tools and validated and applied them in the project. So we have a so-called hybridization tool, which uses a simple control strategy to get the dimensioning of batteries and fuel cells. And on the other hand, once the train is built, we use a tool called Smart Energy and Speed Optimizer for rail, which is able to optimize the speed profile together with the controls of the fuel cells and the batteries in a way that you always have enough power and enough energy available by also influencing the drive power you need, the traction power you need by influencing the speed profile. So this is now more or less what we really did in the project, or the other partners. This is a picture of the fuel cell system. It's a second generation fuel cell system from Toyota, the same that is also used in the actual Toyota Mirai, but of course in a little bit of different layout. These are one of the two energy storage systems provided by CAF. And this is one of the 4 racks of hydrogen storages that are brought to the vehicle, well, with very complex piping, as you can already see here. Everything had to be tested with the controls before, so CAF built a hardware-in-the-loop test bench, especially to show or to test the integration with the train control and management system before it was really operated in hardware. One of the 2 power packs used for the train was built outside the train here in CNH2's facilities in Spain. So we started in February 2022, 14 months after project begin, with building up the first power pack, 3 fuel cells with their cooling systems, the hydrogen monitoring and supply panel, and also one of the storage systems, and a big DC-DC converter to put everything to the 3 kV DC voltage of the train in the end. This test program was, on the one hand, testing the components, but also consumption tests according to standardized profiles by the European Joint Research Center, drive cycle tests, ramp-up tests, and specifically created tests from our use cases and service profiles. And as a result of these tests, we consumed more than 220 kilograms during testing of hydrogen, and we got a detailed knowledge and could, of course, optimize the whole energy management system and prove that the system is working as expected. The other topic was to develop the train demonstrator itself. So this is the CVR3 car that we got from Renfe as a basic electric train. And the aim was to have this one made out of it, a hydrogen train, still having the pantograph equipment there. So We started with the development in 2021. We started with the testing in 2022. In parallel, the second power pack was integrated to the train, and first static tests were done in beginning of 2023. Static test means the train was standing or driving on a closed area. And in May 2023, we received the first authorization to travel on the Spanish network with the full train with both power packs. One of the topics, as I said before, was the refueling of the train. So what does it take to refuel such a train? On the one hand, you need the dispenser unit itself with the lots of valves and safety equipment and so on. But in our case, for 160 kilos per day, the system that was created in the project consists of 4 such containers. So 2 storage containers, 1 compressor container, and 1 dispenser container. And all of this has to be operated to use the train. Yes, at the moment, or for the demonstration of the train, we could only use the dispenser with an overflow filling. And now, as the train demonstration is already done completely, the aim of the project is to validate the full refueling station, which we will do this year until the end of the year. So I have also some pictures, hopefully no sound. So this is part of the testing in Puerto Llano with the fuel cells there, the battery systems that have been on the train, and in parallel the HVAC systems have been dismounted from the roof, and fuel cells and their cooling systems have been mounted on the roof of the train. The energy storage systems have been brought to the middle car, so all the seats have been taken out, and batteries and tanks, hydrogen tanks, have been brought to the middle car. And then we started our first tests on the line from Zaragoza to Canfranc in the Pyrenees. So it went steep up to 1,200 meters. And as you can see, no catenary, no choke. It's purely hydrogen driving there, even in these demanding lines. Yes, in the meantime, our whole testing program has been achieved. So we have not only been testing on this line. We had 4 other lines in Spain and 1 in Portugal, making this train not only the first hydrogen train on the public network in Spain, but also in Portugal. We could also do an autonomy test, which was in our case 800 kilometers on hydrogen purely, plus unlimited with the catenary, of course. I was asked to put together some of the facts. So the train demonstrator itself is a 3-car unit with the 3 kV pantograph DC system. The energy storage systems range up to a max power of more than 1 megawatt. Not on the wheels, but of course on the energy storage. Quite small compared to the power they can deliver. We have 6 of those 2nd generation fuel cell modules from Toyota, which are rated 80 kilowatt each, and 160 kilograms of H2 storage on the vehicle. In our case, it's type 3 storages, which is not so critical for refueling, like the type 4 with the temperatures. And that's good because we have higher temperatures in Spain and had higher temperatures during testing sometimes. We have been driving now more than 10,000 kilometers in hydrogen mode, about 6,000 in electric mode, consumed roughly 2 tons of hydrogen, and could prove this autonomy of a little bit more than 800 kilometers. Yeah, that's it so far as a short overview. If you are interested, you can have a look in all these videos on YouTube where a lot of the different phases are described. And that's it so far from my side. Thank you.
Thank you very much for this insightful presentation of this project, which was also very successful, one has to say. It's a huge task to implement such a train. Also some questions we will ask you in the Q&A regarding this. This brings us to the next presentation, the last one for today. regarding hydrogen internal combustion engines in the rail sector from Roland Fortenbach from Bosch. Thank you for your presentation.
Yes, thank you very much, Nikolaus, for the introduction. So my name is Roland Fortenbach from Robert Bosch company in Austria, and I would like to bring another aspect into the discussion today, and that is about the hydrogen ICE in the rail sector and the international trends that we see there. So the work that I'm presenting is funded by the European Union as well as the Austrian ministries, and this is something that I would like to mention right in the beginning. I structured my presentation in 5 chapters, so I would like to start with an introduction of Bosch as a company and the solutions that we provide there. Then I would like to talk and to continue with the transformation challenges as we see them in the large engine market, together with some rail market flashlights that I would like to share with you, and then coming to the paths and technologies and solutions that are provided by Bosch. I would like to close my presentation with a summary and conclusion. So first of all, looking at the company figures of Bosch, in 2023, we had sales revenue by more than 90 billion euros, together with more than 400,000 employees. And our business is structured into 4 business sectors. So this is the consumer goods with the washing machines as you know them, with the energy and building technology sector, as well as the industrial sector known by Bosch Rexroth, and the mobility sector, where is my home base, and this is also the biggest sector that we have at Bosch. Then, looking at Bosch in Austria, there in 2023 we had a sales of 1.4 billion euros with 300 and 200 associates. And looking at the locations that we have at Bosch, my home base is located in Hallein, where it's also the headquarter of the business unit Large Engines. And looking at today's place here in Innsbruck, this is quite in the neighborhood. What is special about our business unit Large Engines? I mentioned already that we are located in Hallein, and there we have our manufacturing plant where we are manufacturing the fuel injection equipment for the large engines. And what we also have on site is all the functions that we need to perform the business inside this large engine business unit. That means we have the management on site to take decisions. We have as well the sales and project management on site, as well as the engineering. That means that we have everything to perform our business in an excellent way. Now we did a zoom from the big Bosch to the plant in Hallein. Looking outside, we understand ourselves also as a part of the hydrogen economy. That means we are providing and developing products for the hydrogen value chain from the production, storage and distribution, as well as the usage. And in my presentation today, I would like to talk about the hydrogen engine. Continuing with the transformation challenges, this shows an overview of activities and initiatives by OEMs, countries and organizations on the way to decarbonization in 2050. For example, the EU Fit for 55 program, or in the US, the Inflation Reduction Act. This is political work that is supporting the decarbonization and the development of alternative technologies that are needed for that. And it is our understanding that we are in a development and assessment phase since several years, and we are expecting on the way towards 2030 a decision towards the technology that will be used then later on in the field and in series. On the very top, I mentioned activities from our customers and end customers in terms of demonstrations in the field. So also they are testing and assessing the technologies that are available at the moment. Second message here is that we do not only need the technology for decarbonization, we also need the political framework. This is also very important, and for sure the infrastructure whenever we talk about alternative fuels like hydrogen today. This has to go hand in hand, and this is also very important. Looking now into the decarbonization targets around the globe, this slide on the right-hand side shows with a color yellow the countries that have a decarbonization target by 2050. And the color orange, for example, or wherever there is no color, that means that these regions do not have a CO2 target yet, or that the target is beyond 2050. And for us, that means, looking at our sales figures, that means 44% or more than 40% of the applications that we are providing, they do not have even a CO2 target. So there is also a lot to do from a motivation perspective. Looking at the railway market, I mentioned here the biggest rail operators in North America and their decarbonization targets. And when we look at that graph, we can see that they have very ambitious targets and also in the very short-term future. So that means that they are looking for technologies, how they can reach the targets that they work on. Coming back to the market and the market flashlights, whenever we talk about large engines, we talk about engines that have a power output more than 560 kilowatts, and we differentiate our business and our fuel injection equipment into 4 application segments. The biggest one is the power generation, another one is construction and industry, also maritime is an application segment where we sell our components, and today I would like to talk about the railways, the locomotives, and also there we provide solutions that we have. Looking at the market, this large engine market is for sure a niche, especially when we talk about automotive and Bosch. So in numbers, that means that last year, for example, more than 70,000 new large engines were built. This is not that much, but looking at the fleet and the value of such a large engine, it means that more than 1 million engines are in the field, and also they ask for technical solutions to decarbonize. And this is also motivation for us to provide solutions there. Whenever we talk about large engines, we talk about harsh conditions, and on this picture, this freight locomotive, this is indicating that we always talk about high load, long distance. So the conditions that we have to provide and have to apply for are hard. Also in terms of criteria like fuel purity, air purity, durability is very important. Noise and vibration emissions, and for sure also efficiency is a topic where our solutions are evaluated. Why is this important, the high load, long distance? Because the majority of greenhouse gas emissions is coming from the freight locomotive operations, and therefore they need durable solutions. The flashlights, looking at today's agenda, we heard a lot about hydrogen and fuel cell solutions, and this is something that I have as well here as a flashlight from Canadian Pacific. But looking at the other flashlights from Wabtec, for example, an engine manufacturer from North America, they are also testing hydrogen engines, the hydrogen combustion engines, and doing first evaluations and developments there. And this is exactly where we would like to refer to, or I in my presentation would like to refer to. Looking at the paths and technologies that we provide for that. So looking at the very top, the blue one, this is showing our diesel portfolio, and the decarbonization also started there with biofuels and drop-in fuels. And our current portfolio is ready that these biofuels or drop-in fuels can be used. So this is a first step in decarbonization. Whenever the targets are higher, we need to look at alternative fuels, like I mentioned here with hydrogen, as well as the methanol and ammonia. And these fuel candidates established to be the future fuels from our perspective. And for these future fuels, we are developing a new portfolio. And looking at today's topic with the hydrogen, we have several technical solutions for that. So from the left-hand side to the right-hand side, they are having increasing complexity. So the easiest solution is using a large engine gas valve, which is easy to also retrofit, and then it has also the opportunity that it can be used in a dual fuel engine, and that gives also additional robustness in terms of having the alternative fuel infrastructure available. Whenever we talk about higher engine performance, we are coming to the alternative fuel injector with a direct injection and the low pressure. This is also a solution that we provide and work on. And if the targets are even higher, we're talking about high pressure equipment and also a pump that is providing the fuel at the relevant pressure. Our experience, and this is also something that I clearly understood in the presentation of my colleagues earlier, is that we do not have one solution that fits for everything, but the solution is strongly depending on the segment that we have. So for us, it's power generation, construction and industry, or rail. And not only that we are also looking into each use case, what is the appropriate solution that our customers are asking for and where they need to have technical solutions for. So that means whenever we are in discussions, we evaluate, are we talking about a retrofit of the existing fleet? Then an easy port fuel solution can be the pathway, because it gives additional robustness against infrastructure. Or if we talk about new engine builds and the requirement on the engine performance, then we go to technical, more complex solutions, like, for example, the direct injection at low pressure. And this is exactly the products that we are currently developing for such applications. Again, we inside the Bosch organization are a niche providing solutions for the large engines like we have in the railway applications, and we are serving the complete value chain. So whenever we talk about solutions, we also have to think about the generation of the hydrogen as well as the storage and the distribution. And also there we have something in our portfolio that can be used for making this happen. Coming to the summary and the conclusion. So the decarbonization has already started, and the introduction of specified drop-in fuels is there. This is good, and from my perspective, it will be there also in the future, because this is easy to realize. The new technologies that we are working on is on port fuel and low-pressure direct injection for the alternative fuels like hydrogen. Depending on the segment and even the use case, there are different preferences given, and from our perspective, the decision on the technology will be in the future towards 2030. And within this demonstration and assessment phase, we also expect a consolidation, because at the end of the day, we need some scaling effect as well, and not too many individual solutions. And our focus is on port fuel and low pressure DI injection for hydrogen combustion engines. Thank you very much.
Thanks a lot for this insight also into hydrogen combustion engines used with hydrogen and this possibility. We heard already that there is a huge stock of existing cars where solutions are needed, so maybe this can also be one for these issues. We have now already heard about 3 hydrogen trains that are operating in Europe. We started with the test of the Coradia Eland from Alstom. Stadler is already showed their Flirt H2. And then we got an insight on this European hydrogen project, this train from CAF. There is a 4th train also available in Europe from Siemens. Siemens was unfortunately not able to join us, but they sent us a promotional video I want to show now. So just a short impression of this train. And as we already heard, refueling of the trains is a big issue, since we have a lot of hydrogen on board compared to passenger cars, but also heavy-duty vehicles where we are in the range of 40 kilograms at the moment. So here we are the range of several hundred kilograms. And here, regarding the Siemens train, also the Green Energy Center Codex partnership met with this train, with the refueling station, which was developed by the Wolfgang Group and EDC. And this was used to firstly refuel also the Siemens Zug when it was on the way on the Bavarian tracks. And this is also a development which was formerly made for the hydrogen snow groomers, another project that started here several years ago, where we had to tackle this question how to enable refueling of heavy-duty vehicles with high hydrogen demands in a also budget manner for tests like we have it here. So this also closes the loop, and we got now this overview over the 4 important hydrogen trains in Europe, and we can now conclude with the questions Q&A session. Please, Lars Behrendt, Stefan Bernsdorf, Holger Titus and Roland Fortenbach come to the stage and let's answer the questions then. Some questions already regarding ÖBB and test operations. I mean, obviously, ÖBB decided to not go for hydrogen. Why do you think that other train operators use hydrogen trains? Where's the difference to the ÖBB use case?
Okay, the ÖBB use case is we have a short range of diesel traction lines, so this means we have no long distance passenger service as diesel traction, it's just in commuter railway. And the second is the profile, the mountain profile of Austria. So you have, if you the most diesel traction going to the mountains, and you are able to rolling back to the main line with a recuperation energy effect. So that's an aspect you have to consider. So it means in a flat long distance line, it makes sense to use hydrogen operation, but in the most part of Austria, it's maybe not necessary.
Okay, thanks a lot for this insight. We have now seen this Stadler train, if we go to Mr. Bernsdorf, in operation in the US actually, or which will be in operation in the US. Are there also projects in Europe you're working on?
Yes, we have 2 projects in Italy on narrow gauge that we're currently working on, in Calabria and in Sardinia.
And what are the main differences from normal gauge to narrow gauge if we consider hydrogen trains?
The inherent difference between narrow gauge train is you have a smaller profile, so you have less volume, less footprint available for putting systems in, and that is an additional challenge really to laying out the vehicle on the fundamental engineering in the first step for the layout. Also, the axle loads tend to be lower on narrow gauge rail, which is also a challenge and restricts you on putting very heavy equipment like traction batteries in abundance into the vehicle.
maybe a question for my own interest, is the drivetrain, this technology, is it very similar to this Flirt H2, or did you make a lot of, do you have to make a lot of changes, I mean regarding fuel cells, refueling our tank system and so on?
Fundamentally, the system is very similar. You've got a fuel cell system of a number of fuel cells that really depends on the operational need, that provides a current to the traction converter as is needed. You've got the battery. To me personally, a hydrogen train, as mentioned before, is really a battery train with a hydrogen range extender. And that principle doesn't change. So you need to find the right balance. It is different for every application. And that's an interesting challenge for our engineers. So there's obviously differences in terms of architecture and layout, but the fundamentals, they're the same.
Thanks a lot. Which brings us to the project of DLR, and what I've seen, it's quite comprehensive in terms of testing and so on, what has been made. Is it also planned to bring these technologies to a production or to a product?
Not in this project. So for CAF, I think it's part of their hydrogen strategy to test such a system and to get it done and know all the challenges that are behind of something like this. As far as I know, they are doing other projects already in France together with other OEMs and other operators. But this train, as it is, was just a demonstrator to show that the concept of such a power pack is possible. And now we are also in the challenge to rebuild it to its original state. So we shall not only show it works, we shall show that it's possible to build it back to the original state.
Interesting. Yeah, as you could see, or Mr. Kometer showed that in the HyTrain project something similar was planned with this diesel electric train to convert it to hydrogen to have some knowledge gains there, but this will be, or has to wait for a next project to happen actually. Was it possible to do that within the HyTrain project? Maybe a question to Bosch. We now show that there is you showed that there is a lot of potential in regards of internal combustion engines with hydrogen. Is there already a concrete project with OEMs and customers going on? Is this in the planning stage, or where in the stage of realization is what you showed?
I mentioned that we have quite a lot of activities together with our customers on testing our equipment in first single cylinder testing, and I think it's important to mention that a hydrogen injector is not coming from the shelf, so there is also development work needed, and the first step is combustion development, and there we are in several activities together with our customers. Next step would be on the way to validation, confirming these results on the multi-cylinder engine, and then at the last going into a demonstration phase to also prove in the field that this solution is working. So there are a lot of activities going on, yes.
I see. Do you also plan to retrofit existing engines, or is this really a new development?
Retrofitting engines is also a use case where we look into. And whenever we get an inquiry on that, we look very detailed what are the boundary conditions, and then we decide do we want to step into or not.
I see. One question to Stadler regarding the fuel cell system. Did you also plan or make use of the waste heat from the fuel cell system, or are there any plans regarding this? We heard already there are some energy losses. Mr. Behrendt showed that from the energy introduced a lot of energy is excess heat actually, which maybe could be used, maybe not in California, but somewhere else. Do you plan to do anything with this, or is this actually not so easy?
Maybe for common understanding, that one of the challenges with a fuel cell is compared to a diesel engine, that all the heat generated by the losses, they have to be actively cooled. The diesel engine, they get rid of about half of the heat generated via the exhaust gas. And the efficiency is in the same order of magnitude. So we have to install a lot more cooling. Ballpark figure, double the cooling capacity for the same installed power for a fuel cell. And it's not at a very high temperature level. So if you were to make use of the waste heat, it wouldn't be very efficient because you don't have big temperature differences. So we did look into that on a very principal level early in the project as well, and pretty much discarded it for now. Mainly also because we neither had the time nor the available spare volume. It's not like a train is, oh yeah, there's an extra room, we don't know what to do with it. We put passengers there. So it's, we didn't see a lot of benefit in it, and we didn't go down that path anymore.
Interesting, or thank you. So there is, maybe for the future, there are possibilities, but yeah, well explained why you decided for the current cost, or to not include it yet, at least. As far, I already said I saw some other presentations of colleagues from DLR. You did some studies on heat recovery, right?
Yes, in the project we have one thing is WAPTEC Fabulay is analyzing an absorption HVAC machine, which makes cold heat stream, or whatever you call it, from the waste heat, which is quite challenging because the temperature level is quite low for such a system. And my colleagues at DLR, they are thinking about using the waste energy in the hydrogen storages. So you have potential energy of 350 bars, and you need 10 bars at the fuel cells. So you need to get rid of that pressure, and you can use it to create heat or cold in metal hydrates. And if you use two reactors in an exchange process, then you have continuous heat or continuous cold energy. And this is part what we analyzed here, to have really the real hydrogen consumption and put it on our test bench and see how much hot or cold energy could be created. And it's in the level of like 10% of the electric energy you would get as a heat stream, cold or warm in the end.
Interesting.
Still with not too much temperature, that's the problem again.
Yeah, also in the HyTrain project we looked into some possibilities to use this excess heat. It's, as you all said, it's not so easy to do it, but there are some options that may be beneficial for the future. So also Team Paisenta, Post, and there was a concept also developed on this issue. You now also already brought us to storage. In our project, the hydrogen is stored in pressure vessels. If we come to hydrogen combustion engines, hydrogen storage also in pressure vessels, or do you also think about other possibilities?
So this packaging of the overall solution is always coming from our customers and end customers. And the technical solutions from a storing perspective that we currently see are two different pressure levels at 350 and 700 bars. Or if we talk about applications, for example, in the power generation segment, there the expectation is that the hydrogen is coming from the infrastructure, the future infrastructure.
I see. Maybe one advantage from internal combustion engines over fuel cells, which are used in all the other four trains, is the hydrogen purity. What kind of purity do you need for your hydrogen?
So, in general, the purity requirements are lower whenever you talk about usage in the combustion engine. And the criteria that I put on my slides, that are always comparing fuel cell solutions together with ICE solutions, they are very much depending on the boundary conditions that you use to look at it. So I would like to leave this rating at the partners that have to take the decision if they want to go for a fuel cell solution or a internal combustion engine solution.
Okay. So maybe to come back to ÖBB, you had your test runs. So in general, what do you think are the best applications for hydrogen trains?
Okay, the best, in my opinion, the best application for hydrogen trains are long distance services, and for railway tracks, they not have an electrified system. They have long distance, and they have not how should I say it? Sorry. There's a lot of space, so you have long distance, a lot of space, and long distance between big cities. That, in my opinion, is a use case for hydrogen trains.
So if in Austria, so to say, the lines would be different, then it could be maybe a use case, but it's really depending on the profile of the tracks.
It's depending of the profile. As it's depending on the, for example, also the electricity mix of the power generation. There a huge aspect to have to be considered to make this decision for pro-hydrogen.
I see. Let's come to another question to Stadler. So there was a question asked in the chat. What is the maximum allowed weight for the hydrogen storage system? It's going a bit into that direction. Also, how much hydrogen can be stored on this flirt H2? What is the storage capacity?
The first part, the weight is really determined by the maximum X load we design for. The bigger challenge were the batteries. If you look at it, they're quite heavy per volume. The fuel cells and the hydrogen tanks, they weren't a big challenge really. On the inventory of the vehicle, I'm not sure if that is a public figure. So it's enough for 2,800 kilometers on a good day.
I see. If a customer would need a higher range, so to say, is that possible within your...
Yeah, we designed it, the power pack, in a way that it can be scaled, it can be made shorter or longer. So we at the moment designed for 3 different steps. The one we built into here is the medium size power pack. You get a small and a large, and it comes in increments of storage volume. The large one would be double the volume as to the small one.
I see. And then, as you said, it's really huge trains until 12. Did I hear that correctly? 12?
That's on the Flirt family.
Okay.
So what we've done, the longest one is for the UK market. That was a 12-car consist. Not Jacob's bogies all the way through. 6 and 6. We've got long ones in Switzerland as well with 8 cars. But we don't see large vehicles like this as the typical application for more niche low frequency, low customer applications like battery or hydrogen. Typically, again, that's just an average statement, but typically when you have a high customer demand, you have a business case for an overhead power line as well. So the vehicles we're talking about today, hydrogen, touching sometimes on battery as well, they tend to be smaller vehicles. So we are looking at 2 cars, which is the smallest we're doing, up to maybe 4 or 5, something in that range.
I see. Thank
And then you always have, as an operator, have the option to do double traction in peak hours. You put 2 of the vehicles together and you have 1 driver.
I see. Okay. Yeah, thank you for clarifying these options. No, it's quite... I understand. Let's come to the refueling. Also in the DLR project, we saw that there was also a refueling station, or you showed a refueling station. Was the refueling station developed within the project?
Partially. So our partner CNH2, they had parts of it already. So this dispenser container was available. It was from another project where they also, it's also able to refuel at 700 bars. So it has 2 dispensers. There was an additional storage brought to that existing concept, and we made it for less pressure. In the end, we don't need the 700 bars. We are not able to refuel at 700 bars, so we went down to the 350. Yes, but it was also with other, I don't know, regional funds. They already had other projects, so some existing equipment and something on top. It was the most difficult part because here we really had problems in delivery chains. Things didn't work the first time and then you needed a separate part or something like this and you couldn't get it. So this is why we have a delay in the refueling station. There we really came into topics of delivery, supply chain challenges.
I guess everyone here already tried to order a fueling receptacle and didn't get it. Yeah, this is just one.
And the PLC for this and so on.
And it's also extremely expensive.
Yes.
Yes, you already mentioned. Okay. Regarding the Type 3 storage tanks, so you have a metal inliner, aluminium inliner, or?
I don't know.
Okay.
Type 2 is aluminum.
Do you think?
It's metal, I know, but I don't know which metal.
Okay. Regarding, do you think this is beneficial in regards to refueling times? Or what was that? Why did you actually decide?
I think it was a question of availability at that time. It wasn't the aim of the project to develop storages, so it was searched for something that is applicable for rail and usable for rail and already available on the market.
I see.
For the refueling, it doesn't make a difference because the standards for refueling limit the vessel temperature to those 85 degrees, and they don't care if it's type 1, type 3, type 4 as far as I know. So we are also limited to those 85 degrees, even if such a storage could handle more temperature.
Well, that of course, we also did a lot of, or we worked a lot on the refueling protocols. So for trains, there are no refueling protocols per se.
Yeah.
And of course, type 1 temperature is not an issue. And as Nusha also mentioned, there was a refueling protocol for this train, or for this HyTrain developed, to refuel within half an hour, especially with a lookup table, and also to the main issue. Of course, you always can refuel fast if you pre-cool, but which costs money. And so the question was, within the target time of 20 to 30 minutes, if we don't pre-cool, when is it feasible? So because there's some money in it, and yeah, it's quite a tricky thing actually, this refueling, and it's for trains not that available yet, but what is for hydrogen on the other?
Yeah, we don't know exactly on the vehicle side with the storages. I guess you have the same concerns with the temperatures. then there is no refueling protocol, and also the question of communication between the train and the refueling station could be quite helpful to have a communication, but it needs to be safe in CL4 level in the end, so it's difficult to do all this at the same time.
Do you have communication?
We have no communication. There was a point where it was decided we don't need it. Later on, maybe it would have been better to decide different, but we don't have it. I know that Deutsche Bahn in the H2Go's Rail project, which they are currently showing with Siemens, they have a communication.
Maybe for the audience to explain, if you have a communication, you know the temperature inside the tank, and therefore you can refuel faster. If you don't know the temperature within the tank, you have to go with lower speeds in order to be safe. That's just the issue. Why communication is a thing, but since it's not standardized, everyone has to develop an own system. I have one more question for Bosch, or actually two. There was a question if it's also feasible to burn mixtures of fuels. Maybe not. So if one had, or is this something that is considered, or you say, okay, we try to get under control burning pure hydrogen, burning.
Yeah, that's the focus of the today's work. I showed that there are also other alternative fuel candidates, like for example methanol or ammonia. And there it's also in discussion to use hydrogen, a little amount of hydrogen to improve the burning qualities.
And then one last burning. You said burning quality.
Yeah. Important to mention. Let me make one more remark. Is that many hydrogen applications are today natural gas applications, and there it's always possible to use a certain amount of hydrogen together with the natural gas.
I see.
So this would be also an opportunity.
This would also be feasible.
Yeah.
Since it's a combustion engine, you burn at quite high temperature, and there is also always some NOx coming out of it. What are you doing in this regard, or what are the solutions?
Yeah, that's right, and this is also the focus in the combustion development that I mentioned earlier in my answer. That this is the first step to improve and optimize the combustion, and the nitrogen values is for sure something where our customers look in detail at. And when I mentioned that there are 2 plants in Hallein, the second one is providing denoxtronic, and that would mean that you have an exhaust gas treatment afterwards, if the amount of nitrogen is too high.
Okay, so there are also possibilities to work against this. Regarding the fuel cell system of which was used in the DLR project, in this train you said it's a Toyota fuel cell, also used in the cars. So it's not a specialized heavy-duty fuel cell. You did a lot of measurements and so on. Is there anything you can say about life expectancies and so on?
These are still under analysis, the real life behavior and the duration, but here we have to rely on the values that are given by Toyota. All I know is in this testing campaign we haven't seen any degradation yet. So it's good, because if we would already see something after this small amount of kilometers, then we would have a problem in the future, but still it's more or less begin of life condition anyway.
Okay.
Maybe on degradation, what we learned during the project, the biggest problem is impurities, and it depends on the technology of the fuel cell membrane, but they are very sensitive to that. So that can have a really big impact. So hydrogen quality is a big topic, and quality assurance during the daily operation will be a topic. And in my personal view, maybe at the moment a little bit underrated topic still.
It is. I think you're completely right. I have to say that because we are actually currently working on a project called High Quality together with the ÖVGW, that's the Association for Gas, Water and Gas in Austria, how to implement a monitoring and quality assurance system for hydrogen, because in the end we saw in the HyTrain project, it's then always the question, whose fault is it? And if there is no clear data, I mean, it's really a problem for both sides. So it's very important to have this quality of the hydrogen well defined, firstly, but also well monitored, and then to see where are the problems. Because as far as I also understood from your projects, we are at the very beginning, and regarding lifetime, we don't know everything yet. So it's a path that needs to be gone together, actually. Yeah, quite interesting. Are there any more questions from the audience?
Maybe no question, but a remark, you should mention that we are driving hydrogen cars since 10 years here in the Green Energy Center, and have the first hydrogen car in Europe. It was installed here, and we have some experiences with fuel cell, so that there's not the impression that there's nothing in there about this hydrogen quality and so on. It was one of the first questions in general when we imported the first cars in Europe. Yeah, how the quality of the hydrogen must be. So, and I can remember there were big discussions in Bolzano about this issue, and now we are driving these cars 10 years already. We have more 2 generations of cars here in the center, so we are driving all the day with this hydrogen cars. So it's an input for you as industry, so that this is a very important point from the quality assurance aspect and from the risk management, but on the other hand, we can see the cars are driving.
So what I had to learn, I think that was an important point, the cars, they drive, so it's reasonable, it should also work for a train, and that was also, as I say, my personal approach. And what I learned in these last 8 years, we all learned a big train, and that of course in the train it's much more complex because you have those long lifetimes you need to guarantee. The car, okay, if one of 3 or if one of 100 cars breaks, it's reasonable, but for the train it's not an option, it has to go. And you don't have these big numbers, you have these long durations, it has to work, you have the business cases over 30 years, you have to supply all the maintenance parts, and what we saw in the HyTrain project with the fuel cell providers, okay, they want to sell volume, and in the train you don't have that, so it's a really not so easy thing with the train and the fuel cells and the hydrogen. But in the end, if all the parameters are correct, and if you find the right project, as we saw, can be really an interesting case.
And the operators should know at the end of this day that they cannot sell this via internet, this technology.
Yeah.
So this is one big message which is really for me it's the main issue, because I can see nearly everybody thinks he can sell this in Amazon.
Or buy it on Amazon, right?
Or buy it in Amazon.
Okay, good. So technology is still in the future in some ways, although projects already exist and products already exist. Thank you for giving us this insight and also answering quite detailed questions, actually. I know that this is not so easy, since yeah, some or a lot of information is actually quite confidential to all the partners. Then, thank you all for participating, everyone who participated online, people participating here, all the speakers, of course. It was really nice that everyone made the effort to come here to the Green Energy Center Europe, be in place. I hope we can use now some minutes to also get to know each other better. I also want to thank the team of WIVA for supporting. I want to thank the team of Fence Systems, which was a lot of work to organize this event. All the HyTrain consortium partners, of course, and the technical team from Audiwerk also for doing such a nice job with the technical issues. So thanks a lot for everyone attending this knowledge exchange. I hope you learned something, and if there are any questions, and if you want to operate a train, just write, right? info@hytrain.at, and these experts, a lot of knowledge is here. You cannot buy it on Amazon. See you hopefully soon. Bye everyone.
Thank you.